Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thanks a lot, Anna, for the nice introduction. Hello, everyone. A very good day, and thank you for joining to the AI for Good Machine Learning 5G Challenge webinar session. My name is Thomas Bascolo from the ITU, the International Telecommunications Union. The Machine Learning 5G Challenge aims to create a community to solve network-related problems using AI and machine learning. And today I'm very excited to host a webinar, which is a technical talk titled Lessons Learned in Radio Channel Measurements and Modeling, Promising Opportunities for Deep Learning for Physical Layer Wireless Communication Networks and Sensing. This talk will discuss radio propagation channel characteristics and modeling approaches. And the discussion will span the spectrum from below 6 gigahertz to millimeter wave and terahertz bands. Of course, with a special emphasis or special focus on AI and machine learning opportunities. I'm really happy that today we have a renowned speaker, Professor Ted Rappo, who is a professor at New York University, as well as the founder and director of NYU Wireless, which is a multidisciplinary research center focused on the future of wireless communication and applications. He has several accolades to his name, and he has received several awards. He's an inventor, but also he was elected to the Wireless History Foundation Hall of Fame in 2019. He received the IEEE Summerfield Award in 2020. So many awards. I'm so glad and happy to have you, Ted, with us. Good morning to you.
Good morning. Thank you, Thomas. It's good to be here.
Thank you so much. So I leave the floor to you. So please take it away.
All right, great. Thank you. I'm going to share my screen, and delighted to be invited by ITU's AI to Good. I'm a wireless expert. I'm new to AI and machine learning, so I hope to learn with you, but I hope to provide a useful talk on some of the lessons I've learned during my life of research in wireless and how they might help with AI and ML. Before I go, I just want to make sure, is the audio and the video okay?
Yes, all good.
Okay, great. Well, thanks again for the invitation. What I'd like to do is be able to move my slides, and there I go. Okay, so first what I'd like to do is talk about the move to millimeter wave and sub-terahertz. I'll show why it's inevitable, but I want to ask the question, is it safe? And I think AI and ML can help us in this realm and in other medical realms, and I'll motivate why we're going to higher frequencies. But this talk is not just about millimeter wave and sub-terahertz, it's about the fundamentals of the radio channels, because if we're going to do machine learning for wireless, we have to understand the fundamentals and the models. And so I'll provide some promising channel modeling approaches that I think could really help the AI and ML community, and then I'll conclude. So first, I want to talk about safety. You might be asking, why is Professor Rappaport talking about safety? After all, we did a lot of research to verify and validate the safety of millimeter wave back about 10 years ago. And just the history of wireless communications, cellular, for the first 4 generations of cellular, operated below 6 gigahertz on the far left of the radio spectrum in the microwave range. And then in 5G, it's the first standard that moved up to millimeter wave. We did a lot of the pioneering work over 10 years ago to show the world that millimeter wave, moving from about 2 or 3 gigahertz up to 30 gigahertz, could allow much greater bandwidths. And people wondered, was that safe? Well, that was 5 orders of magnitude below ultraviolet and X-ray. It was 5 orders of magnitude below visible light. We know that ultraviolet, X-ray, and gamma rays, we know these are dangerous. In fact, if you look at NASA, one of the big 5 worries of sending a human to Mars is exposure to galactic radiation. But if we're well below the visible light, there's no known effects other than heating. In fact, we wrote about this, my colleague Chris Collins and I, where we have appointments in the School of Radiology at NYU's Med School. And with graduate student Ting Wu, we demonstrated through all the literature we could find around the world, and there was a lot known about millimeter wave. Was it safe? And the only thing we could ever find repeatably in the literature is that thermal damage could occur. If you had thermal damage to tissue, to human tissue, to cells, or you had a very, very high level of temperature raise in the body, that could cause mutation of cells and cause abnormal cell growth, which of course is carcinogenic. But other than thermal heating, we could never find any problems. However, as we go to terahertz, as we move again another order of magnitude, say from 30 gigahertz, today's 5G, up to 300 gigahertz, which I'll show is very viable, we're still 4 orders of magnitude below ionizing radiation, where the particle of a energy propagating wave can knock out a valence shell. We're still 4 orders of magnitude below, but are we sure it's safe? And there's very, very little known about terahertz compared to the millimeter wave. So my question is, can AI and ML help us with safety? And I have been giving this talk now for about a year, where I always make a point to ask government funding agencies from around the world to start looking at objective research on lab rats, lab animals, tissues, human growth, to see if there's any damage to terahertz with terahertz radiation exposure. It's 4 orders of magnitude below, but I'm thinking that deep neural networks might be able to help, first of all, find out in the literature, is safety concern only due to thermal? You know, can we search that? I haven't done that. Can AI and ML be used to help us in experiments, in measurements, in understanding if terahertz is safe? And then moving up to the ionizing radiation in the world of the medical imaging and of course space travel, where we get above the troposphere. God made this amazing 10-kilometer and below protection for the Earth. It's called the troposphere. When you get above 10 kilometers, you're in space and you're bombarded by galactic radiation, which is dangerous for us. Can we use AI and ML capabilities to monitor real-time radiation exposure in ionizing settings, such as the CT scan or the X-ray or the PET scan in the doctor's office? I want to be clear, terahertz and millimeter wave, they're non-ionizing. They're 4 and 5 orders of magnitude below ionizing radiation, which is known to, in long serial doses, to be carcinogenic. Radiologists have reported on this in international studies, that the cumulative ionizing radiation can be dangerous. But wireless, as we use it, is non-ionizing, 10,000 times lower in frequency and at the energy where things become ionizing. But can we use AI and ML to help us in all these realms? It's a question I have, and I think it's an open issue. So let me dive into the talk, motivations for millimeter wave and sub-terahertz. I've been doing a lot of work on that, in fact, for since 1998, so that's been 25 years, probably even before that. And the bottom line is, we're going to move higher in carrier frequency simply for this fact alone. Narrowband circuits, filters, and antennas are very easy to build in mass quantity, at low cost, inexpensive, and reliable when you use a typical 1% bandwidth about the carrier frequency. So if you look at wireless today in 4G, cellular carrier frequencies are about 2 gigahertz in the microwave region. A 1% bandwidth is 20 megahertz, which happens to be the channel bandwidth of a 4G LTE channel. And similarly, going up to 5G, 28 gigahertz, a 1% bandwidth is 280 megahertz. So you can make very economy, low-cost devices with wider band channels as you go up higher in frequency. So what could we do with a 1% bandwidth at terahertz? Well, at 1%, that's a 10 gigahertz channel. A narrowband channel is 10 gigahertz wide. That's a lot of bandwidth. And I'm going to give you a context of how much bandwidth 10 gigahertz is and why we might want it. So this is the bottom line. Moving higher in carrier frequency gives us more capacity, more bandwidth very easily. Now in 4G, we're using concatenated channels. So you can concatenate 4 or 5 or 7 20 megahertz channels together to get 140 megahertz, which is much wider bandwidth than the single LTE channel. So concatenated channel bandwidths are popular and a way to get bandwidth, but the way to get more raw spectrum is to go higher in frequency. And the discovery of millimeter wave being viable, which we led at NYU, really was kind of like what oil fracking did for the oil industry. It brought a whole new source of energy into the planet, and millimeter wave brings a whole new source of bandwidth going up higher in frequency. Because you look at the spectrum, as we go higher and higher in frequency, there's more and more carried bandwidth at a higher carrier frequency. So let's look at the human brain and human computing. God gave us this amazing brain. Each of us has a 30-watt brain, and we have about 100 billion neurons firing 200 times a second asynchronously. It's the world's greatest parallel processor, and each neuron's connected to about 1,000 others. Now, when you think about our speed of computing, that's 1,000,000 billion computations per second, or 20 petaflops per second. We're computing it in communications terms, 20,000 terabits per second, if you consider a machine operation to be a bit. 20,000 terabits per second is the data rate of our brain, this amazing, massive parallel processor. And each of our neurons is writing to at least 1,000 others. And it's not necessarily binary. We don't really fully understand it, but assuming a conservative binary mode for writing to each neuron, we're talking about 100 terabyte hard drive each of us have. So that's what we have as humans, each of us. It's a miracle, I think. And when you look at what $1,000 buys today, and this is based on work going back decades ago, which still holds over a century of computational. Today, in our smartphone, for about $1,000 US, we get about 1 trillion computations per second. No, 1 billion. No, we're at 1 billion computations per second. And what that means is we have these amazing multi-threaded CPUs, and we're computing these things in our smartphones, in our laptops, tablets. But in 2036, if you look where this projection is, by 2036, $1,000 commodity pricing will buy us computation that's on the order of the human brain. That is, we'll be able to do this 20,000 petaflops computation and commodity pricing in under 15 years. So let's consider that. Can we remote the human brain? Can we remote the real-time computation of humans? And if you consider wireless in 2036, when we have commodity pricing for human computation, if we use this 10 gigahertz RF channel bandwidth, 1% at 1 terahertz, and we use 1024 quadrangular amplitude modulation, which we already are doing better than that. In 5G, we have 4096 QAM, so we're already doing 4 times more capacity. But assume a very modest 1024 QAM. And then we've got to somehow get 1,000 times more somewhere. Maybe it's beyond massive MIMO, some new antenna technology. Actually, we don't need 1,000, we only need 250, because we've already got 4 more on the modulation going to 4096 QAM. So 250 times somewhere else, that gives us a physical layer over wireless of 100 terabytes per second, terabits per second. That is 0.5% or 1/200th of the human brain, 100 terabit per second data rate. And if we have 100 gigahertz channels, either through concatenated channels or wider spectrum access, we get a petabyte per second of transmission, or 5% of the human brain real-time communication over the air. And there may be other wireless breakthroughs that increase link speed. This is remarkable. We talked about this in 2019 in our paper, Opportunities and Challenges. And I call this wireless cognition. Now, while this is not intelligence, it is the ability to transmit in real time very, very high speed data, which is comparable to the computational rate of what we do. So wireless cognition through artificial means will be viable. Now we look at the state of the art in AI, and while there's a lot of hype around ChatGPT and large language models, there's tremendous work going on in visual AI, using video and visual imaging for artificial intelligence. And Meta released the segment Anything, which is trained on 11 million images. And when you think of the computation time needed for learning and training these models, these deep neural networks, it's pretty remarkable. A single image needs 100 gigs of computational multiply and accumulates. That's a lot of computation, but it's on the order of what will be commodity pricing, as I just showed. The exciting thing is we can use wireless to transmit back these images and use edge cloud computing to do a lot of the building and processing and learning and upgrading the models. These huge bandwidths will be a boon for AI and ML as it becomes part of the fabric of our world. Let's look at another visual AI released by OpenAI a couple of years ago. Again, very large vision model, 3.5 billion parameters in these models. These models have billions and billions of parameters, as you know. And again, this wireless connectivity through 5G, wideband, 6G, 7G is going to allow this wide bandwidth pipe to edge cloud computers that are in the base stations, perhaps. And the base stations will be densified, as I've talked about in other talks and have written about. We'll have the small scale movement, which will move base stations closer and closer to people, lower power, much denser, kind of like Wi-Fi access points. That's where wireless is going as we go up to these wider bandwidths. It's also more power efficient, as I've written about. So this is where the infrastructure for wireless is going that will carry these. And then look at a couple of large language models released earlier this year, Llama and Falcon, one by Meta, one by UAE. And these models are huge, billions of parameters, but pretty exciting early results. So the infrastructure of wireless as we go up to these wider bandwidths, millimeter wave and sub-terahertz, will power this, this revolution. Now, one of the things I really want to point out, it's important for everyone in the field, I think, to be very cognizant of, is power consumption. The ICT industry, information computer technology, communications technology industry, we're going to be huge consumers of the global power grid. In fact, we'll be about 1/4 to 1/3 of the power consumption of the planet, our wireless industry. And so I really want all of us to be mindful when we're building these models and building the computations. We need to really be economical with power consumption. Is it worth it to spend hundreds of watts to get an answer to a problem that could be answered with 1 watt of power? And is the power being used over the wireless network? Is it being used in the edge? Is it being used in our device to charge our device? All of these things need to be considered. So we've developed a theory called the consumption efficiency factor and the waste factor. We published on it recently, which tries to put a mathematical framework on quantifying power used. We do it just for a wireless network for now, but we should be able to do this for CPUs, for memory, versus computation, versus parallel processing. We should be able to, the GUI, we need to really get a way of having a metric that we all talk about, that we all standardize on how much power is used. And we've tried to do that with the waste factor and the consumption efficiency factor. And we demonstrate how this is really fundamental, just like Harold Free's noise figure was fundamental 80 years ago. And now all wireless devices, when you buy a receiver, you know its noise figure. Every noise figure every receiver in the world, every mixer, every amplifier, every front end has a noise figure. We can talk to each other as engineers on what the additive noise is, because 80 years ago, noise was the enemy of wireless communications. Well, the enemy of our planet is going to be our consumption, our needless consumption of power. So having a much more solidified and agreed upon metric that we can talk about on how much is being used to make these wild computations or to use a wireless network, we need to have that. And so we've proposed the waste factor. and the consumption efficiency factor. It's very much like noise figure, but it's waste figure in a cascaded communication device. Anyway, I'm not going to talk about that here, but I do want to just point out that we talk about it in this paper and show how the densification of cellular networks are going to make wireless much more efficient on an energy per bit consumption. So you can read more about the details here. Anyway, the FCC, seeing all this, and I was fortunate to be able to talk with them about our research. They agreed to open up spectrum for the first time in the US above 95 gigahertz a few years ago. It's called the Spectrum Horizons license, and for the first time in the US, there are 4 unlicensed bands. And you can see down in the bottom right corner, we have, for the first time, bands allocated for unlicensed devices that start approaching this 10 gigahertz wireless cognition realm. And there are companies making products right now. There's investment happening. And the FCC is viewing this as a way to see, just like in Wi-Fi, in the early days of Wi-Fi, unlicensed bands were provided before the mobile industry moved into commercialized cellular license bands. Same thing will happen here. So we're moving to the first time above 100 gigahertz, where we're going to have these giant wideband communication channels. And when you have this kind of bandwidth, you can imagine the applications: autonomous cars, drones, robotics, this idea of wireless cognition. We talk all about this in our 2019 paper. But the bottom line is we're going to have a lot of network offloading, and we're going to have a lot of cloud work. Of course, we rely on the cloud for these AI ML models. They're very, very hungry computationally. But we're going to need to figure out how to distribute this to the edge. So AI shores at the edge of the wireless network within a few 100 meters or 100 meters of the mobile user. This is going to become part of the future. And we've talked about some of the applications, seeing the dark cameras, personal health monitoring. All of these capabilities will be available just in your handset and with the use of edge computing. Very accurate location. I'll talk about that in a minute. But the bottom line is there's huge amounts of opportunities with this information shower. Information shower is this idea I've had for about a decade, where wherever we go, we have this huge multi-gigabit per second data rate, allowing us to upload, update, carry our information with us, being delivered from the edge or from the cloud. And we see that starting to happen. We see how software is so much now a service from the cloud, not necessarily carried with us. So this will only continue to perpetuate as these bandwidths become wider in the cellular and the wireless world. Now, mid-band spectrum is also very important. These are frequencies below millimeter wave. These are more conventional. We're the first 4 generations, the first 40 years of cellular were operating 1, 2, 3 gigahertz carrier frequency. Mid-band is kind of moving up from 5 to 10 to 15 gigahertz. And China just announced a 5G spectrum allocation. I think it's at 7 gigahertz. So they're really the first nation to authorize a lot of mid-band spectrum for cellular communications. It's kind of funny, the US went from low microwave, sub-6 gigahertz, and jumped to 5G millimeter wave, and then has kind of come back to bring mid-band. All the spectrum is vital for wireless carriers, but you just don't have as much raw bandwidth capability at mid-band as you do up at millimeter wave and sub-terahertz. In fact, you see the FCC commissioners last year talking about it, where last year the FCC chairwoman, Jessica Rosenworcel, was talking about identifying spectrum in the 7 to 15 gigahertz range. And then you had another FCC commissioner, Commissioner Carr, talking about the importance of mid-band spectrum, again, in the 7 to 8 gigahertz range, but also spectrum above 95 gigahertz, including terahertz. So you can see the FCC is kind of looking to provide the carrier capacity for this massive wireless cognition capability that's coming 10, 15 years from now. So the talk I said was going to be lessons learned and how we can help AI and ML, deep learning and deep neural networks, how we can help them. And you know, I've been studying this stuff for most of my life, and I love it. And there's so much expertise of decades before I even became a grad student that built the fundamentals of wireless. So asking a machine, the computer, or thousands of computers in parallel to learn this stuff when we as humans with our God-given brain take so long to learn. It's very tricky. So I'm going to try to provide some fundamentals for those of you who are not wireless engineering experts like me. Maybe you're an AI ML person, maybe you're a computer programmer, CS, you don't know much about wireless. I don't really know the scope of this audience, so I'm going to try to keep it general. But the bottom line is there are some fundamentals, and I want to give kind of a little bit of the background of where I've been, my journey, and where I think there are some really golden nuggets that the AI ML community can use and learn for advancing knowledge that is artificial intelligence about radio channels. Radio channels are vital. I mean, think about the miracle of our cell phone. We can walk and talk and do internet and texting in a very bizarre environment, a stadium, a house, an office, driving down the street in a rural field. It's really a miracle wireless. And there's some fundamental issues about the radio channel that either make that link work or don't. And trying to learn that and improve it and make our power more efficient and make our networks more efficient is one of the great opportunities of AI and ML. But to be able to do that, we have to understand the fundamentals. So I want to take us back to really where the theory of wireless started by Harold Freese. Harold Freese is one of my heroes. He was a Bell Labs researcher, and he wrote this paper in 1946 called A Note on a Simple Transmission Formula. And here in this equation 1, he shows that it's the antenna gains and the distance and the wavelength that really determine the received signal strength between a transmitter and a receiver. It's in free space. Harold Freese is spelled differently than free as in free space, but he really came up with the equation that tells you how much power you will receive divided by the power that you transmit. And it's a function of the wavelength, the carrier frequency, the distance, and here's that d squared term you'll hear me talk about, distance to the square. It turns out it's just the surface area of a sphere. Remember the volume of a sphere is 4/3 pi r cubed. Well, I take the derivative of that, and you get 4 pi r squared as the surface area. That d squared comes from the surface area of a radiating. Think about blowing a bubble of bubble gum. You blow that bubble real big. Well, the amount intercepted by a little receiver on that bubble gum is going to be smaller and smaller as that bubble gets bigger and bigger. So as you go further in distance, you get smaller surface area that gets picked up by your antenna at the receiver. And that's what Harold Freese realized 80 years ago. And we still use this. We still use this in all of wireless cellular engineering. It's a fundamental, what's called large scale path loss. The distance and the frequency and the antenna gains determine how much receive power you'll receive. And so I say in the beginning, this large scale fading effect is simply capturing the area from this omnidirectional antenna. And on the right, you can see what's called large scale and small scale fading. This is a narrowband receiver. We don't use them anymore. We're all very wideband. We have directional antennas, but back in the early days, it was an omnidirectional antenna and it was a narrowband channel, a few kilohertz voice bandwidth, or FM 30 kilohertz bandwidth, very narrow channels. 1G was 30 kilohertz bandwidth, 4G is 20 megahertz bandwidth. It's a move of over 1,000 in capacity going from 1G to 4G. But you can see on the right, the signal is getting weaker and weaker in that dark curve as we go further away from the transmitter. The transmitter receiver separation's on the bottom. And so we're getting weaker signal as we go. And you can see the rapid fading or small scale fading happening along that motion of the receiver. And here you have Free's free space equation, very famous, right here. And you see the d squared in the denominator. That d to the 2 or 20 log d is free space path loss as you go further and further away in free space from the receiver. Now, along with large scale fading, that is the receive power, there's small scale fading, where in the early days of cellular, 1G, first generation, 1970s and 80s, we had a mobile phone with an omnidirectional antenna, and the omnidirectional antenna received energy from all these different locations as multipath. We didn't know where the multipath was coming from back then. We didn't have directional antennas like we do now to figure out where the rays are coming from, where they're bouncing off. All the rays of energy came in to the mobile antenna and caused this fading, Rayleigh fading, because Rayleigh fading is many unresolvable paths with the same average power. And a lot of pioneers, mainly at Bell Lab, wrote about it and created the fundamental theories of small scale fading. So here you have the two fundamentals, large scale and small scale fading. And when I did my PhD in 1988, I went into factories and I found fading as I moved the receiver in a factory, but it didn't have this big deep fades like the other Raleigh fading. It was Rician fading. In fact, it only had maybe depths of 10 or 15 dB. I didn't have these big deep Raleigh fades. This was Rician fading. And interestingly, when I plotted the distribution of the received envelope, it was indeed Rician fading. And I want you to see that the path loss in the factories didn't have that n equal 2 or that d squared. It was d to the 1.8, or it could be as high as d 2.6 or d 2.8. So this is interesting. And by the way, this work led to Wi-Fi. This was they used this research for the first Wi-Fi standard back in the late 1980s. And what's amazing is, and this was the first paper I ever published. And so here we were with line of sight and non-line of sight offering different path loss, large scale, not d squared, but d to the 2.6, d to the 2.8, we find it be higher. And we realized that wireless propagation is very much dependent on the site-specific nature of the environment. I mean, that's how energy gets from the transmitter to receiver, just like light gets to our eyes based on what's reflecting and what's obstructing. So we did a lot of work on ray tracing. In the early 90s, we had parallel computers, Spark computers, dozens of Spark computers all processing the massive amount of computation. Some great students working on this. Kurt Schaubach's now the CTO of Federated Wireless, a CBRS spectrum sharing company in the US. And we did this simple idea of shooting rays out and bouncing off of the surfaces. You had to model the surfaces, you had to model the environment. And Scott Seidel went inside buildings and he could get very, very accurate predictions with assuming some basics on the building materials and locations. Very, very accurate. You can see on the right, in fact, look at the measured versus predicted path loss. That's the received power using propagation modeling and just computing the power in each of the rays that are bouncing. And then the RMS delay spread. This is the multipath spread, the amount of time delay in the channel. It's very, very accurate, you can see. And that's really, really, that was very encouraging back then. We called this site-specific propagation prediction, and it was very accurate. In fact, the world gravitated to it over time, and it's now used in standard wireless planning. But I want to give you the story of how I knew millimeter wave would work, because no one was thinking about this in the late 1990s for mobile. We were thinking about it for fixed point to multi-point when the FCC, under Reed Hunt, the chairman, opened up LMDS spectrum at 28 gigahertz to try to provide a local exchange carrier competitor to wired line. The idea is you'd have these directional point to multi-point antennas house to house from large towers to provide this massive bandwidth over millimeter wave, much greater than you could do for buried cable at the time. Of course, DSL came and disrupted that, and the circuitry was too expensive in the late 90s. But in this measurement campaign we were doing for LMDS, we discovered that when it rained, the line of sight path was attenuated, as you know happens at millimeter wave. But this is where I knew millimeter wave would happen. When I saw that the reflection off of the ground between two buildings, when I saw when the water landed on the pavement between the two buildings, my reflection path changed at a different power rate than the line of sight path. This was staggering to me, and it's when I knew millimeter wave would work. Of course, I couldn't tell anyone. A few people I told thought I was crazy because you just couldn't do it. They said never happened. People never thought you'd go above 6 gigahertz in wireless. I've seen that all my life. And of course, I'm going to show you we can go to a terahertz. But notice how when the line of sight path faded due to the rain attenuation, the multipath signal in high rain increased. So I got an increased multipath signal while I was having a decrease in the line of sight. And this told me that there's a lot of diversity, a lot of angle and time delay diversity capable in millimeter wave channel. Turns out the ground actually got more reflective and was a good source of energy. Unexpected result. So I did this indoors and found out there's amazing spatial energy that comes from all these different angles of arrival. So if you had a directional antenna, you could actually couple this energy and make very reliable paths, reliable wireless systems. Even when the line of sight path was blocked, you could bounce off the other things. And so we predicted, this is the first paper in the world where mobile is mentioned. We submitted it before some other papers by other places and predicted that millimeter wave mobile would happen in 2011. And then we proved it on the campus of UT Austin in 2011 and 2012, where we went out to put a base station up on the roof. This is at 28 and 38 gigahertz for this study. And we found there was amazing amount of energy. Look at all the links you could make by spinning that antenna around. Basically, you could look everywhere. If you were down in that urban canyon, you could spin your antenna almost anywhere and find energy. You wouldn't always find it, but most of the time you could make a path. So the idea of having an outage due to millimeter wave, we showed experimentally that it looked like you would not suffer tremendous outage. And then, of course, this paper in 2013, the It Will Work paper with an exclamation point, the only paper I've ever written with an exclamation point, proved it. And then we went out above 100 gigahertz, where we've put the idea of wireless cognition and this idea of using massively dense antennas, hundreds of antenna elements to start getting this amazing directionality to capture the energy, harvest the energy, and to do things like sensing and to do imaging, see in the dark, behind walls. So this kind of bandwidth gives us, and this is key for the ITU seminar today with AI and ML. This is what I think is very exciting for you to be able to conduct the work in AI and ML. It'll give you the pipe, the mobile pipe, in order to keep building the models and to fuel an improvement in accuracy of AI and ML. I guess one of the important things to think about is this. In the whole world of wireless, starting from the early days of Freeze and then Jakes, we're in the first time at a point in wireless with 5G cellular where we have two dimensions, two new parameters, dimensions of freedom that we never had before. These two new dimensions we have are super, super narrow time duration symbols or bits. We have very wide bandwidth channels, which means we have very, very small time duration symbols and bits. That gives us great time resolution, traveling time. We can use bits to sound the channel, and we can do channel sounding as overhead on our wireless. And then the second thing we get is we get the narrow beam widths, because we're going up to carrier frequencies where the size of the wavelength to human freckle. We can build very, very directional antennas, so we can do very, very good angular resolution, spatial resolution. So for the first time ever, we get a very high degree of time resolution and very high degree of space resolution built into the cell phone, built into the wireless network. And we talked about this for position location. You can do amazingly good position location if we have a map of the environment on the cell phone or at the edge. That is, if we have some site-specific information, and you don't need a lot, but a little site-specific information, you can use these two new degrees of freedom, time and space, to get very, very good position information. In fact, you can see by exploiting the multipath, where it's coming from in direction and when it's coming in time, this time and space allows you to get with relatively low base station density, and the deployment cost is medium because we assumed it's expensive to put maps everywhere, to deploy maps, to download maps, to have the maps of where you are. You can build the maps like breadcrumbs, but the accuracy is very, very good. You can see it's very high accuracy when we talk about that. So I want to debunk the myth right now that we won't be able to go to these higher frequencies, because a lot of people still are skeptical about going to millimeter wave. Governments won't allow millimeter wave. They're worried about the health effects. We tried to debunk that myth with everything we knew in 2015, and that's safe for generations to come. Safe for generations to come, show there's no health risk. We're 5 orders of magnitude below ionizing radiation. But look at this. Look at the curve. This is showing frequency going out to a terahertz, and this is attenuation in dB per kilometer. The whole world first 4 generations were down here at the far bottom left of the curve, where the oxygen and hydrogen. This is just what's in our air beyond free space loss. Free space transmission loss that I showed you from 1946 says that the wave disperses and you lose power. This is the additional loss due to oxygen and the atmosphere. And you can see pressure, temperature, and height above ground matter on how much additional loss you get. And we never thought about this at first 4 generations because cellular was always down here at sub 6. But you have these resonances of molecules in the air, and these peaks, these high attenuations are oxygen, hydrogen, water atoms that cause the channel to become lossy. This is why the 60 gigahertz bandwidth was unlicensed 20 years ago, 30 years ago, because there was this 20 dB per kilometer loss. So the FCC felt it was safe to allow unlicensed stuff there because it can't go very far. But look at most of the frequencies at standard sea level. You can go out to 400 gigahertz, and you're only 20 dB per kilometer, the same as this 60 gigahertz. And 20 dB per kilometer is only 2 dB per 100 meters. And that's where small cells are going. There's that size in cities today. So over 100 meters, you only lose 2 dB in addition due to the atmosphere than you do at sub 6. And either way, all the way out to 900 gigahertz. Look at that. We're maybe 100 dB per kilometer, which is only 10 dB per decade, or per 100 meters. So we're only going to lose 10 dB on a 100-meter small cell at 900 gigahertz. I think wireless will go to 900 gigahertz. I think that's it. We're going there for wide bandwidth communications in the next 10 to 15 years. Physically, nothing stopping it. Rain's not stopping it, because once you go above 70 gigahertz, you've designed the 5G cells, all the rain rate, because the rain's drops are bigger than a wavelength. Rain doesn't hurt you any further out. So once you've designed for 70 gigahertz, you've designed out to a terahertz. So look, you can get a couple of kilometers easily on millimeter wave and sub-terahertz. And I talk about this in a killer app. I think 5G's infrastructure build is going to lay the foundation for 6G because of the small cells and the adaptation of millimeter wave. I won't talk about this very fast other than to show you that it does get tougher to penetrate things the higher frequency you go. And this fundamental formula, which we wrote about in our textbook in 2015, shows you that the received power actually goes up as frequency goes up. I want to say that again. Received power goes up as your frequency goes up for a fixed distance, as long as you keep the antenna apertures the same in the comparison. You see, free space loss of 1946 showed the antenna gains. And those antenna gains are a function of the wavelength and the physical area. So if you keep the physical area of an antenna the same and you go up in frequency, that antenna gets more gain. So double directional antennas, where the transmitter and receiver both have directional antennas, not omni, you get more received power, not less, at higher frequencies. So that's great news. We've done tons of measurements. We have over a terabyte of data of real measurements of impulse responses, channel received power, channel time delay, angle of arrival. We make these available for our industrial affiliates. They have our terabyte database. All the industrial affiliates have them. We're thinking about broadening that access, but we have data in these millimeter wave channels, indoor, outdoor, in buildings, massive database. And some of the amazing finds that I think AI and ML can use is, the great news is that path loss, large scale path loss, the received power over distance, has really a remarkable frequency independence. That is, it doesn't matter what carrier frequency you're at, as long as you use a 1 meter free space reference at the first meter and use free space path loss with the lambda squared and the d squared, and you scale to that first meter, the slopes of all the measured data at all these different frequencies have the same slope. It's 1.4, that's less than 2.0. Remember, in the factory back 35 years ago, I found 1.8 in the factory with omnidirectional antennas. These are omnidirectional path loss synthesized. 1.4 at millimeter wave, you're actually getting wave guiding, ducting indoors. And then 2.66, pretty close to what I measured in factories, in non-line of sight. And it doesn't matter what the frequency is. And over here, I show you the comparison of two models, two path loss models, to predict the received power. One's called the close-in free space distance model, the CI model. The other's called the CIF. It's a weighted path loss exponent as a function of frequency. And what we see is frequency didn't really matter. It doesn't matter what frequency you're at, as long as you take out the first meter. This was pretty good. The empirical versus theoretical was in a few dB. So this is very exciting. It's a very good path loss model for channels over the entire millimeter wave and sub-terahertz band. And I claim from 0 to daylight in wireless. That is, this is very similar to what I saw in the factory building, and very similar to what was measured in the 80s and 90s in the first generation, second generation of cellular. The path loss exponent really doesn't change from first G to 5G to 6G using a 1 meter free space path loss reference. And then this is spatial clusters, energy coming from space. There's 4 different spatial locations on average, 4 distinct resolvable spatial angles at 28 gigahertz, and that goes down to 1.9 as you go higher in frequency. So you lose some of the spatial diversity as you go higher in frequency in an office building. Same with non-line of sight, but there's still energy to be found at different directions. That's great news. And in the time delay, you get more time dispersion, more multipath coming later at lower frequencies than you do higher frequencies, but you still have energy arriving 11 nanoseconds after. So you have multipath happening. This is due to partitions. I won't get into the details, but we have a lot of models now, and we have these massive data sets of propagation in all these environments. And when you go outdoors, it's very similar. By the way, we've made all these models available in a Monte Carlo simulator called NYU Sim. You can download it for free. NYU Sim's used, it's been downloaded over 100,000 times. It replicates real world channel impulse responses. It's not site specific, there's no map tied to it. But if you want to get an idea of what these channels look like and over their statistical variations, it will produce sample functions based on the terabytes of data we've measured. It's a free resource. Hundreds of companies and universities are using it. It's used in their 5G modem development, and it goes now up to 150 gigahertz. So you can use it up to these frequencies that we've measured. It's all measurement-based statistical models. And when you go outside, it's just, I really admire the students. They're really these great explorers that go out and do all these measurements. We find amazingly the same thing. And we have the benefit of putting the transmitters and receivers at the same locations over the last decade on the campus of NYU in Brooklyn. And we measure the impulse response, the received signals, the path loss, the time delays. And we see what causes reflections. You know, these things are very good reflectors. They're also very good obstructors up at higher frequencies. And again, the same thing. We find that the path loss exponent is remarkably non-frequency dependent, which is great news. And here again, we see that the CIF, or the close-in frequency dependent path loss model, really isn't needed. We don't need that extra model complexity, because the close-in model, that free space model with the first meter, and then just looking at the path loss beyond that first meter, we can see, look at the red, 28 gigahertz. You look at the slope of the red diamonds, that's non-line of sight, the best non-line of sight data. You look at the slope of the bubbles, at all the different frequencies, it follows the same slope. They're all about 1.91, a little bit better than the D squared. So it's D to the 1.91. And then in non-line of sight, for the best non-line of sight, it's a little worse than indoor. It's 2.96. That's when you have a path. If you have an outage, you have an outage. But this is once you've got a path and there is no outage. So these models are all based on not being an outage. So of course there's statistical outage models. I won't go into that here. And that's where ray tracing helps, because it lets you see where you have a line of sight or the ability to make a path. In fact, ray tracing is used for coverage planning generally in the wireless industry, and has been for a long time. So here's what the spatial angles look like when you look around in space for angle of arrival and angle of departure. And you can see, similarly to the indoor building, outdoors, you have in line of sight a decay of the angle of arrival. But amazingly, in the omnidirectional non-line of sight case in the outdoor environment, you don't decay too much. you still have a large number of angle of arrivals happening in the outdoor channel at 2873 and 140. So we've got all these models available in NYU Sim, and we have the raw data. So, and delay spread again goes down, typically goes down. There's one place where it went up. This was kind of funny. At the directional line of sight, we explained why in the paper. It was an anomaly. We're actually able to see something reflective that wasn't in the channel back years earlier. But the bottom line is these millimeter wave and sub-terahertz channels work. And I put a bunch of papers in here if you want to learn more about the various things we've talked about. But and we just finished a book with some of the people at NIST and some of the active researchers, Andy Molish and Alenka Zajic in the US on radio propagation measurements and channel modeling best practices for millimeter wave and sub-terahertz. Now, that's a lot of stuff. And that's kind of what I've been doing the last few years, but I want to spend the last couple minutes talking about some promising findings and models. You think about the radio channel, and it's like this, it's like an elephant. When you make a measurement in a wireless system at a certain point in time, it's like trying to look at an elephant. You're only seeing a tiny part. So how can AI and ML, a computing, artificial computing platform, figure out, model, and understand what's happening in the channel by just taking a snapshot, a zero-shot measurement? How do you do that? Well, ray tracing is the holy grail. It was originally developed for computer graphics. I've been working in it all my career. It's a very powerful tool for site-specific channel prediction. But as you know, it has tremendous number of parameters to model properly. Every wall, every ceiling, every signpost, every carpet. We're making an open source ray tracer, NYU Ray. I'm on my second generation of graduate students. We'll make it available for free when it's done, just like we did NYU Sim. It's based on our terabytes of measurement, but for AI and ML, we need a simpler problem, I think. Ray tracing provides a site-specific model. It's very accurate, but it's huge computation. So can we simplify the channel model and extract some useful information? Let's let AI and ML tackle first something easier, and I think we can extract some amazing channel properties from some simple models, some simple fundamental results, and I want to point them out to you. First is this work by a brilliant student, Greg Durgan, who's now a well-known professor at Georgia Tech in the RFID and wireless power space. Greg really did some amazing theoretical work, and we came up with new analytical models and probability density functions. Probability density functions are important for model building, of course, and what we found is this new model distribution called the Two-Wave With Diffuse Power, TWDP, not a very sexy name. I'd like to call it the Durgan distribution. TWDP is the case where you have two waves that are specular and diffuse everything else. Now, Stephen Rice, when he came up with the Rician distribution, had one specular component and everything else was diffuse. So this is two multipath components and everything else diffuse. And so not surprisingly, it is Raleigh and Rician as special cases. And it's finding a lot of use now because in millimeter waves, you saw that there's two, generally a minimum two good angles of arrival. And there's generally a couple specular components that you can find in millimeter wave. That is, there seems to be always two in these wideband channels that we use today. There's even more than two, but there's always at least two. So here's a way to encapsulate narrowband and wideband fading and signal behavior in new ways. And it's entirely characterized by three parameters: sigma, K, and delta, and they're all intuitive. I don't have time to go into it, but what the beauty of this TWDP distribution is that it models Raleigh, it models Rician, and then it models all kinds of weird stuff in between that we could never model. And this is what I think AI and ML needs. It needs a robust, physically based model from which you can build or base your learning from. So I'll just show you some simple examples that you can very easily, with a couple of these parameter values, identify quickly. Is there one specular component or is there two? You get this for free just by receiving the narrowband envelope of a signal. Let me put this in context. The narrowband envelope is the cheapest, easiest thing for a radio receiver to detect. It comes from the 1920s. An envelope detector of a simple CW signal on RSSI. This is the RSSI. By monitoring the RSSI over a little bit, you can determine if the channel's Raleigh or Rician, and if there's one or two waves of specular nature. That could be really useful in AI and ML to figure out what the channel's like and how it's going to change. Then, from that work, we came up with multipath shape factors, which give even more information about a channel that is just using a narrowband envelope. The received signal envelope, like I showed you in the early graphics of the earliest narrowband signals, just by looking at the envelope, you can, if it's near Rayleigh fading, if it's close to Rayleigh, that is, if it's not too deep Rician, and there's a lot of work we can do here to see what happens in Rician. We haven't done that work. Greg graduated and went on to great things, but this is a very fertile research area. By just looking at the envelope, if it's Rayleigh, you can immediately determine where the strongest multipath is coming from. Think about that. If it's near Rayleigh, if you have a signal, you can immediately, from the received envelope, figure out, if you point to the maximum direction of fading, you can figure out where the energy is coming from. And you don't do any pointing, you just figure it out from the narrowband envelope. And if you had two narrowband envelope arrays, orthogonal, think about what you could do. You could start generating information from narrowband. And by the way, narrowband travels the furthest because you don't have the FKTB, B is virtually zero. So you have very, very high signal to noise ratio on a pilot tone. Using a pilot tone and an envelope detector, you can get a lot of knowledge about where the energy is coming from. In fact, you can figure out if there's one multipath component or two that are bigger than all the others and where they're coming from. This, I think, is a very fruitful area for AI and ML. And then finally, I'll end the talk by showing you some measurements we did in 2017 at millimeter wave. We measured students walking across campus. We just kept a transmitter and receiver. I wanted to see what happened when people walked through the antenna. Transmitter was on the left, antenna's on the right. We collected hours and hours of data across a main area of the NYU Brooklyn campus. And here's what we found. It was amazing. You could model a very simple two-state Markov model for when the signal was starting to become blocked. As a person walked in front of the transmitter, you could always saw a little ripple before and after they walked in, and then you saw these ripples going into the fade. And by the way, you can get the speed of the person by the transitions of this waveform. And we found it everywhere. And so we made a really simple two-state pedestrian blockage event. But think about it, using a narrowband envelope. Again, these are narrowband signals, no multipath, simple, low complexity on a carrier. You can measure the carrier envelope, the envelope, say a pilot tone, and you can learn, a machine can learn when you're about to go into a deep fade, when someone's about to walk in front of the antenna. And you could use this to steer and point your adaptive antenna somewhere else. We found it again and again. It's been reported in the literature by others. So I think this is a very exciting opportunity. So let me conclude by saying, it's been a pleasure to be here. I don't know a lot about AI and ML. I'm on the learning curve. I hope you'll help me learn. I'd love to work with you to learn more, but I think we have great promise, first of all, for ensuring safety in the ionizing medical imaging and exposure, maybe in deep space. Let's use AI and ML to help us on the ionizing part. And let's also help AI and ML to ascertain if there are any risks going up to terahertz carrier frequencies. I felt very confident that all the literature we could find at millimeter wave, it was safe, it was non-ionizing. We're going up another order of magnitude from millimeter wave gigahertz up to terahertz. We're still 4 orders of magnitude below ionizing radiation. I just want to make sure it's safe. And personally, for me, I want to make sure it's safe because I feel very blessed. God gave me another life. I survived leukemia in 2015, and I believe it was the ionizing radiation from the CT scans that caused it. And I went back and got the medical records, and I think that safety is really important. The doctors never thought about giving ionizing radiation to an immunocompromised person. So I've had a chance to change the medical world with my doctors in not giving ionizing radiation to leukemia survivors who don't have an immune system, because without an immune system, you can't fight off the free radicals. The extensive work we've done and other people have done since demonstrates the viability of millimeter wave and sub-terahertz. Wireless cognition, this idea of transmitting in human computation speeds, I think will come. I think it's 15 years away. I think edge computing will be a big part of that. Ray tracing, while it's the ultimate in site-specific modeling prediction, I've proposed a few ideas that I think have promise for AI and ML and wireless. And finally, in all of our works, I'd ask that we always be mindful of the power we are consuming. It's going to be more and more of an issue for the planet. With that, Thomas, I'll thank you. I know I hit the time limit. I'm grateful to be here, and I'd be happy to take questions.
Thank you so much, Ted, for this wonderful talk. Quite informative, a lot of materials covered, but very interesting talk. I would like to invite my colleague Vishnu to moderate the Q&A and have some discussion, maybe 10 minutes of your time, Ted.
Thank you so much, Thomas. Yeah, thank you, Ted. It's very, how should I say, uplifting talk, Ted. Thank you so much. Let me just tell you that it's a great pleasure to talk to you, and thank you for coming. There is a bunch of comments which I want to get out of the way. Mark says that Mark has given a set of pointers. Thank you very much, Mark, for the work in UK on IEEE transactions. From mobile, we see total embedded energy. Thank you so much. And then
Hi, Mark.
I think
good to see that, Mark. I'm going to get that reference. I see it's 2022. Right. Thanks. Email it to me.
Thank you. Sure. Yeah, we'll get that done. There are several questions on your PPT. Would you share your? Can we upload your PPT? Yeah, good. Thank you so much. So
yeah,
that
gladly.
Is
as long as I can get it to you. It's like 100 megabytes, so I'll just have to upload it on your whatever your easy to use cloud.
Will do. Thank you so much. So that is out of the way, and I want to also just read out what Yang-Hong Wang says. He has studied your textbook. Thank you. Yeah. I can see that he has told us here that it is.
I need to write a third edition. I know I have to write a third edition. That's one of my goals in the coming year.
Cool. That we will look forward to that. So yeah, I think that's the main set of comments that I wanted to get out of the way. Then there are a bunch of questions. Let me take this one from Mark about the studies on energy per bit for a 500-meter link on 1 gigahertz carrier to terahertz carrier frequencies related to antenna efficiency, analog digital transceiver efficiency. So would you like to take that step, please?
Yeah, I think Mark wrote that too. I'm trying to read the comments here. I haven't done it. We did do a simple example at 140 gigahertz. We didn't do 500 gigahertz. We did 140 gigahertz in that December 2022 paper with the waste factor and the consumption efficiency factor. So we have all the math drawn out and trying to think of all the power consumed. We didn't consider GUI. You know, I think GUI and computing and other things in wireless devices take more power even than the actual link. That's why I want us as a community to think of this holistic power consumption metric, you know, what that metric should be, what should the key performance indicator KPI be. Someone asked about terahertz, and when I say terahertz, I'm 300 gigahertz and above. I personally don't think it's going to be practical to go much above 1 terahertz. Certainly you can't go very much higher because of the oxygen absorption. If you start looking at what the atmosphere, you know, our air does up to a few terahertz, it gets so attenuative from what I understand. So, you know, millimeter wave and sub-terahertz, I think, are virtually identical in terms of channel properties. In fact, I tried to show that. The path laws are virtually identical. The wavelength's smaller, but we're already smaller, less than a rain drop. So really, millimeter wave and sub-terahertz, you know, up to a terahertz or so, I think they're going to be virtually identical except for that first meter of free space. So in terms of large-scale path loss, the amazing results so far. I mean, you know, yeah, I haven't seen a lot of stuff above 300 gigahertz, but so far it looks like the channel virtually is the same as it was in 1G. It's just that first meter of the dispersion. And that's great because we can use directional antennas to capture more energy.
Thank you so much, Ted. I want to take this question from Gaurav. Gaurav is asking about blockage and directionality of millimeter wave.
Yeah, those are the two
His
things.
question is about terahertz. Yeah, go ahead.
I just answered that. I was answering that question. Blockage, it's an issue. As I showed, it's tougher as you go higher in frequency. So blockage will become more, but it's really very similar. So I answered that question.
Cool. Thank you so much, Ted. Actually, Rahul is asking a question which I was having in my mind as you were talking. Ray tracing is preferred over statistical models. Yeah. So this is a really interesting question because we come across statistical models. We have looked at NYU as well. What is your opinion about statistical models versus AI in general and in combination with ray tracing?
Yeah, so that's a great question. Statistical models are vital for modem development. They're vital. You need to have the long tail of channel states that can create enough confidence to design physical layer. So Monte Carlo simulation and simulations using statistical models are the backbone of really creation of communication links. Site-specific is the backbone for deployment, especially as we go to millimeter wave and higher frequencies. It's the backbone for deployment because it allows you to use a computer to predict the coverage ahead of time. And so they're used differently. You use the statistical models, which encapsulate the rare outages and the bad events for channels, as well as the good events, to build the error correction and those kinds of things. And then you use ray tracing for the coverage, for planning, or for determining capabilities of like position location like we did, or sensing. Now, what would be great is if ray tracing computations could be done everywhere and every time, because site specific, as I've been writing about since the 90s, and Mark Beach has too, the team at Bristol, you know, site specific is really as the big elephant, you get all the elephant. So, but that's computationally so difficult. So it really depends on what you want. And if you're trying to learn what's going to happen in a wireless channel, you'd like to know from the signal, is the person going into an elevator, right? That would be a really useful thing. You don't want to have a video camera sending the video of the site-specific person going into an elevator, but if you can determine from the signal, as the door closes, you see a little ripple in the envelope, that's some really good information that says, uh-oh, I might be going into an outage, I might need to switch a path, network, do something different. So that's the example of using site-specific in research or databases in research to train, to then figure out if you can on the fly sample a real signal. So I think site-specific is more valuable. Ray tracing, I think, is a more valuable tool if you're trying to get into the very tiny, minute details of specific situations that you can learn. But I think statistical modeling is valuable if you want to know what the envelope or what the actual performance of a modem might typically be. And you can see all the typical applications. So there's room for both. Someone's asking about accuracy. NYU Ray, there are commercial tools out there. I publish my papers so that the commercial ray trace tool makers can use the models. I talk to the people at Remco. So my work is out there for everyone to use as fundamental knowledge. When we make NYU Ray available, it will be as accurate and as good and as open as I can make it. But, you know, ray tracers are hard to make. There are companies doing this. So, you know, it's student work. So NYU Ray, I don't know how far away it is, but we've published on it. We had a paper at ICC 2023 student. I have a great student coming in, Mingju Jin. He's a terrific grad student. So I'm continuing that work. And there are a lot of people doing ray tracers. I'm not the only one, but you need these kinds of measurements to be able to build good ray tracers. And that's why fundamental measurements always have to happen.
Thank you so much. Can I maybe pick up on one of your comments? You told about data. Can I ask you? Actually, you also mentioned that you have some intentions to, or you have data. So one of the things which we do in ITU is to package this data, put it out as a challenge, get the students and researchers and industry to solve those problems, and basically give out some prizes. That's what we do as part of the challenge. So is there any plan? Is there any plan to push this data, large amount of data which you have, for the benefit of researchers out there? And what are your plans? If not, what are the other plans with the data? Could you comment on? Yeah.
Actually, I've just been starting to talk with officials at NYU about a distribution plan for the data, because we have 14 data sets, massive data sets over indoor, outdoor, rural, I mean, huge data sets, and we realize there's a need for it. So I'm in the early stages of trying to figure out how we do that.
Thank you so much. We will really look forward to that. There are maybe there are some questions which you have already answered. Could you
the RIS is someone asked about retrieval intelligence services. Those are pretty exciting if they don't take a lot of power. We did research, we just published it in ICC 2023, RIS in factory buildings, and it was remarkably good. The RIS, just putting up little passive metal plates of aluminum. We just put aluminum plates in a factory, went to 4 factories, and it raised the coverage by 6 dB on average. It was amazing, and 20 dB if it happened to be in the right line. So RIS definitely works. They have to be very power efficient, and that's the trick to them. Again, I get into our whole power consumption footprint.
All right. I think the applications which you showed as well, maybe one last question related to computational complexity as well. What about real-time inference versus offline analysis there? What is your pick? There are lots of use cases which use real-time and lots of them which use offline analytics.
Yeah. Well, see, this is a real challenge. The computational burden for these models and for AI in general is so massive. It all goes to some central processor or some big giant thing. I think researchers in AI/ML have to realize what the physical layer of wireless is going to bring them and start distributing some of that load to the edge. So I think distributed AI and ML, I don't know if that's a thing. I mean, I don't know the field, but I would say using distributed approaches where some of the models are maybe pretty good at the edge and don't need as many parameters or as many layers of the deep neural network. Maybe you have enough layers at the edge that can get really good enough, and then you get it crisper and better over time with the remote processing, you know, that gets sent back. I think that's how it's going to happen. And I tried to show you where the physical layer is going to know what you'll be able to package, you know, over a few hundred meters from transmitter to receiver.
Great, thank you so much, Ted. Thanks, Thomas. Thank you so much, Ted, for answering all the questions patiently. It's once again, it's a great pleasure to meet you. Back to you, Thomas.
Yeah, and why? By the way, I'm just going through. I don't want to take up too much time, but I want to answer every question. Someone asked, can AI and ML be used to reduce overall SINR of a wireless network? Absolutely. There were some really nice examples shown at the EUCNC conference. It's online. Peter Vetter gave a keynote at that conference and showed some simple examples along with NTT Docomo. It was a nice keynote. That was some very simple examples of how AI/ML can help. And I think that was the other one I wanted to answer. Thanks, sorry. And I really appreciate all the comments from students and other people who have used my research. I love it. Thank you for writing in. It's a real joy.
Thank you so much, Ted, for all these amazing comments, answering all the questions. And I would like to thank Vishnu for moderating the Q&A. So it's time to close the session. I would like to thank you once again for making time to be with us to give this invited talk. We really appreciate you taking your time. I would also like to make some few announcements. As already Vishnu pointed out, in the AI for Good, we also have AI ML competitions that are related to communication networks. So I know that the talk today, most people that have joined are either interested in AI machine learning or you are in the communication network field. So we are kind of bridging these two domains, these fields together. So you can join some of our competitions and of course, help push the boundaries in research related to the bridge of these two fields. As well, I would like also to inform you, we have more webinars. Please take a look at our program page at the AI for Good. And at this point in time, I would like to close the session. So thank you, everyone, and have a very good day. From me, I would like to wish you a very good day. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.